Hello everyone, in this lesson we're going to be talking about real numbers and we're going to be looking to compare rational and irrational numbers and how to identify them. So let's start with a definition. A number that is the square of a whole number is called a perfect square. The square root of a perfect square is an integer that when multiplied by itself is equal to the given number. So what are we talking about? We're talking about numbers like 1, because 1 times 1 is 1, 4, 2 times 2 is 4, so that's a perfect square. 3 times 3 is 9, so that's a perfect square. 16, 25, 36, 49. We can keep going. 121, 144, 169. We can keep going. Out to 361, which is 19 times 19, and 20 times 20 is 400. So from 1 squared, which is 1, to 20 squared, which is 400, those are the numbers, the perfect squares that I want you to be readily familiar with. And even some sneaky ones, like if we looked at the number 9,000. Well, that's a perfect square, and we can readily identify that because it's the same as 9, but the only difference here is that instead of 3 times 3, we would make this 30 times 30. So you can usually pick out some big ones by recognizing them as repeating from some smaller digits. Okay, so let's find the square roots of perfect squares. So it says find the 2 square roots of 25. Well, what is that? How's that possible? The square root of 25. Well, we certainly know that 5 times 5 is 25. But is there another number times itself that would give us 25? Yes, there is actually. Negative 5 times negative 5 is 25. So when we look at the square root of 36, we'd write it like this. The quick way we will write this is positive or negative 6, plus or minus 6. Square root of 1 is plus or minus 1. Ooh, square root of a fraction. Well, the square root of a fraction is really no more difficult than taking the square root of both the numerator and the denominator. So if you take the square root of 1, that's 1. And if you take the square root of 16, that's 4. So this is plus or minus 1/4. Wonderful. Okay, so let's go ahead now and talk about how we can estimate square roots. So if we are looking at taking the square root of a number that is a perfect square, that's great. Square root of 9 is 3, square root of 49 is 7. But what happens if we have a number that's not one of our perfect squares, a non-perfect square? So if we look at estimating the square root of 28, well, let's look at numbers that might be on either side of 28. So the square root of 25 is right below that, and the square root of 36 is right above that. Those are the next perfect squares on either side of 28. So we know the square root of 25 is 5, and we know the square root of 36 is 6. So now let's consider, since 28 is closer to 25 than 36, the square root of 28 is closer to 5 than to 6. So we're going to estimate to the nearest integer. So to the nearest integer, the square root of 28 is approximately 5. And that's all the closer we're going to get. We're not going to try to get down to tenths or hundredths or anything like that. We're just trying to get to the nearest integer. So we found that 28 was closer to 25 than 36. So the nearest perfect square was 25, so the square root of that is just 5. So if we're going to estimate the value of the square root of 38 to the nearest integer, well, we look at 38, and below it is the square root of 36, and above it is the square root of 49. Well, 38 is much closer to 36 than to 49, so this is approximately 6, because that's the square root of 36. Okay, next, let's look at some inverse operations, but we're going to do something new than some of the past inverse operations we've done. So if we're finding a number's square root, finding a number's square root is the inverse operation of the square. So what does this mean? So the square root of 3 squared, the square and the square root basically cancel, and we're left with just 3. So we can use this when solving equations. The formula d equals 16t squared represents the approximate distance d in feet a skydiver falls in t seconds before opening the parachute. the formula assumes there is no air resistance. And this is actually the formula that we would use in a physics class, in a science class. So find the time a skydiver takes to fall 816 feet before opening the parachute. Okay, so we're going to take that formula they gave us, d equals 16t squared. So they gave us a piece of information. It's falling, the parachuter is falling 816 feet. Great. So that needs to go in for our distance. The distance fell. So 816 equals 16t squared. So if you remember from the last time we solved equations, we follow the order of operations in reverse. So instead of GEMDIS, we're going to follow SAD-MEG. So we want to get rid of subtraction and addition first. But this one does not have any subtraction or addition. So we move on to multiplication and division. So we can get rid of this coefficient of 16 by dividing both sides by 16. And when we divide by 816 by 16, we are given 51 is equal to t squared. Okay, so this is where things are new. We want to do the inverse operation of squaring, so we're going to take the square root of both sides. Now, the square root of 51 is not one of our perfect squares, so we can estimate. So if we take the square root of 51, the next smallest square root is perfect square is 49, and the next biggest one is 64. So 51 is much closer to 49, so the square root of 51 is approximately 7. So that means t is approximately 7. So 7 seconds he will fall 816 feet. Wonderful. Okay, so there's a couple more examples that we could try. The next thing we want to talk about, though, is irrational numbers. Irrational numbers are numbers that cannot be written in the form a over b, basically as a fraction, where a is any integer and b is any non-zero integer. We obviously can't divide by 0, so we can't let b be 0. Rational and irrational numbers form the set of real numbers. So there are numbers that are not real numbers. We're not going to talk about those right now. So rational and irrational are two types of real numbers. The decimal digits of irrational numbers do not repeat or terminate. So what are some examples of irrational numbers? Well, the most famous, perhaps, irrational number is pi. Pi is approximately 3.14159 ... and it would keep going on forever. It will never repeat and it will never terminate. Pi is an irrational number. Another number that's irrational is something like the square root of 2. Square root of 2 is approximately 1.414, and I wish I knew some more digits because it almost looks like it's repeating, but actually it continues to change after that, and it never repeats or terminates. Irrational numbers can also include decimals that have a pattern in their digits. And so this often tricks students into thinking that this is going to be a rational number because they see a pattern. So something like 02 and then 022 and then 0222. Even though that is a pattern, it's cool, I suppose, it's still irrational. It's not repeating like 45454545 or just 77777. So the pattern, interesting as it may be, doesn't make it rational. It's still irrational. So how did I know like the square root of 2 was going to be an irrational number? Well, actually, it turns out that for any integer n that is not a perfect square, so some examples are the square root of 2, the square root of 3, not the square root of 4, but the square root of 5, the square root of 6, the square root of 7, the square root of 8, not the square root of 9. We could, jump over that to square root of 10. We could go much higher to the square root of 51 or the square root of 101. Any number that's not a perfect square, if we take its square root, it's going to be irrational. Okay, so let's look at some examples and talk about is it rational or irrational and how do we know? So the first number is 818111. So this is a number that seems to have a pattern, but a pattern does not make it rational. So this is irrational, and it is, I guess specifically, a non-repeating pattern. What about negative 0.81? Is that rational or irrational? Well, for this one, it is rational. And that is simply because this terminates. I didn't see a repeating pattern, but it just stops at the hundredths. So we would know that this would be negative 81 over 100. And that's of the form a over b. Anything that's a over b, anything that can be a fraction, is a rational number. So if it terminates, if the decimal just stops going, it's rational. 1 2/9. Well, even though we said it has to be of the form a over b, we could make this a over b. We could make this 11 over 9. And so that's a over b. So this is rational. Can be written a over b. What about the square root of 5? Well, the square root of 5 is, again, irrational. What would be our justification? It is the square root of a non-perfect square. What about 0.6 repeating? Well, 0.6 repeating, it's a repeating decimal. And remember, we already spent a whole lesson talking about how to convert repeating decimals into fractions of the form a over b. So if it repeats, it is rational. And we can just say repeats. Great. Okay, let's next talk about how to order real numbers. So here we've got a whole list of numbers that some are fractions, some are decimals, some are square roots, some are repeating decimals. Lots and lots of fun here. So to compare them, it's sometimes helpful to get them into common forms at times. So I will kind of pick out some of the numbers that are clearly negative. So I have negative 3/4, negative 0.25, negative square root of 9, negative square root of 5. So above them, I might just make a little note about an equivalent value. So negative square root of 9, when they put the negative out front, that means they really are kind of talking about the negative version of that square root. So this would be like negative 3. The square root of negative 5 is not a nice number. I don't need to figure out what that is. I just need to know that, of course, if it's the negative square root of 5, it's going to be bigger or to the right of the negative square root of 9. And since I know that the negative square root of 4 would be negative 2, I know this is actually smaller than negative 2, so I can approximate that. So if I look at negative 3/4 and negative 0.25, those are definitely closer to 0 than negative 3 and negative 2 are. So the smallest number I have is negative the square root of 9. Now, notice that I put the number in its original format. I don't want to see this simplified format. I want to see that we can order the numbers as they originally listed. So negative square root of 9, then negative square root of 5, then negative 3/4, and then negative 0.25. So that takes care of our negative digits. And then 0 is an easy candidate to knock off next. All right, so we have 1/2. That's definitely less than 1. But what about the square root of 2? You might be concerned for a second, but remember the square root of 1 is 1. So this is bigger than 1 because the square root of 2 is bigger than the square root of 1. So that's bigger than 1. And I have a 1 over here. And then I have a 0.6 repeating. So the 1/2, that's going to be our next smallest because that's 0.5. Then we have 0.6 repeating. Then we have our 1. And then we have our square root of 2. And then finally here we have the square root of 4, which is 2. And that is our numbers in order from least to greatest. So there are some more examples down here below that you can practice taking square roots, finding the nearest integer square roots, solving some equations, determining rational or irrational. I'll leave those up to you to try on your own. Thanks so much for watching, and see you again next time.